Alright, let's start talking about motion in one dimension, and that means that the object is either moving only in the x-axis or only in the y-axis. It's not moving in two directions at the same time. We will get into that later. Alright, so let's go ahead and just define motion first of all, which we have here. The change in a position of an object with respect to time and a reference point. Alright, so reference point, a coordinate system or a set of axes that are used to represent where an object is and how it's oriented. And then displacement, that's an important one since we're talking about motion. Displacement, the length of a straight line drawn from an object's starting position to its final position, which is different from distance, and I'll get into that in just a minute actually. And then velocity, the description of an object's motion relative to time that it took for that motion to occur. So look at this laser pointer here. It's stationary right now, and then if I move it at a certain velocity, it took a certain amount of time for that to get from the beginning to the end, and it traveled over a certain amount of space. If we were to measure those two things, we would come up with the velocity. Velocity is a vector quantity, alright? So that means it has magnitude and direction. So for this laser pointer, we would need to say it has some velocity in the positive x direction. Speed is just the magnitude of velocity, alright? It does not have a direction. So if I ask you what the speed of something is, then you don't have to worry about what direction the object's moving. Average velocity is the equation that I just talked about, where you have the displacement divided by the time interval it took for the motion to occur. So that's what this equation is over here. The average velocity is equal to the displacement, or the change in position, over the change in time. Also, when we write a variable and we put a bar over the top of it, that means the average of that variable. Please do not confuse that with putting the half arrow over it to symbolize that it's a vector. Okay, these are two different things. Alright? So let's talk about the difference between distance versus displacement. The distance is the amount of space between 2 points, and like I already told you, displacement is the length of a straight line between the starting and ending position. So let's say we have like a course for a 5K or something like that. And the runner starts here, alright, and they travel this path over to this point here. The amount of space between their starting and ending positions is the distance that they traveled. Alright? If you want the runner's displacement, that's going to be different from their distance. Their displacement is the length from their starting position to their ending position. So you can definitely see that these two values are going to be much different than each other. If you have in a classroom a person who stands at one corner of a row of desks, and they run down that corner and around this way and up, around, let's say they come all the way back here. Alright, let's discuss what their distance and their displacement are. Okay? So first of all, let's take a look at their distance. They traveled 5 feet down, then they traveled, let's say we've got 1, 2, 3, 4. So each of those are worth 2.5 feet each. So he moved 5 feet down, 2.5 feet over, another 5 feet, 2.5, 5, 2.5, 5, 2.5, 5, 10, and another 5. So when we add all of that up, the total distance he traveled was 55 feet. Alright, So we can say distance is equal to 55 feet. Now let's get his displacement. Remember, the displacement is the length of the straight line between the initial and the final position. The initial position was here, the final position is here. So his displacement is 0. And you do not put a unit on the number 0, alright, so you don't have to write feet or anything with that. So hopefully you can tell the difference now between distance and displacement. Alright, so coming back to this equation here for velocity, we've got that it is the change in position, also known as displacement, over the change in time. This equation here is something that you've seen before. It's the slope of a line formula, alright? So going back to Algebra 1, y2 minus y1 equals x2 minus x1 equals the slope. That's exactly what you have here. X final is the second position, x initial is the first position, and then you have the second time and the first time, which gives you average velocity. That means that if we were to plot points on a graph, graphing position versus time, the slope of that line would be the velocity of the object that we are graphing the motion of. So let's take a look at that. Alright, we have a position versus time graph. Alright, so on the y-axis we have position, and on the x-axis you have time, and that's always how it's going to be. Remember, the x-axis in science is always for the independent variable, and the y-axis is always for the dependent variable. Time is always independent of everything else. Nothing changes time. It just keeps going no matter what. Position, though, can change. It can stop and it can start, but time can't do that. Alright, so, and then you'll notice that this graph happens to be in centimeters for position and seconds for time. Remember, though, your SI unit for position is actually meters, okay? So, let's take a look at the object. It started off at the origin, which we'll call 0. And then, after 0.1 seconds, the object had moved 20 centimeters. After another 0.1 seconds, we're at 0.2 seconds, the object moved another 20 centimeters to 40 centimeters. So notice the difference between here and here is 20. The difference between here and here is 20 also. So it moved the same amount of distance over the same amount of time. Alright? So if we look, just maybe call this our final position and this is our initial position, and plug into that formula for the average velocity. It's going to be the final position minus the initial position. And so looking down here, actually I guess that they're going to say the initial position is 20 instead of 0 for the origin. So 40 centimeters minus 20 centimeters equals 20 centimeters. That's this change in displacement right here. Or excuse me, change in position, which is displacement. And then 0.2 seconds minus 0.1 seconds equals 0.1 seconds. That's this change in time right here. So the slope of the line between those 2 points is the average velocity. So we get 20 centimeters divided by 0.1 seconds, and that's going to be 200 centimeters per second as our velocity. What is that in meters per second? Let's see if we can figure that out. Alright, you've got 200 centimeters over 1 second, and 100 centimeters equals 1 meter. So these centimeters will cancel out, and we'll be left with meters over seconds. So that's correct formula. 200 divided by 100. These zeros cancel out, and so you're left with 2 meters per second. So whatever this object is, the velocity just in this little section right here is 2 meters per second. Now let's look at the graph overall. You'll notice that this line here is a straight line all the way along. So even though we found the velocity just in this little section, we can actually go ahead and extrapolate and extend that along the entire line. The velocity of the object was 2 meters per second the entire time that the object was moving. Okay, so what can you say about the velocity of the object? If it was always 2 meters per second, what can we say about the velocity? That's right, the velocity was constant the whole time. Alright, so anytime that you have a position versus time graph and the line is linear, that's telling you that the velocity is constant. Alright, so suppose we graph the motion of a boat that's moving at a constant velocity. You'll notice we'll call this the origin, the starting position. He hasn't moved yet, and we have the time at 0 seconds. After 1 second, the boat moved 10 meters. Another second, the boat has moved 20 meters, and so on all the way out to 5 seconds. Now, take a look at the position or the amount, the displacement between every second. 10 meters here, then we've got 10 meters here, and so on and so forth. You'll notice that every second the boat is moving 10 meters. So that gives us a constant velocity. The boat is traveling the same displacement over every second. Alright, so here's our graph. After 1 second, 10 meters, 2 seconds, 20, so on and so forth. So the slope of the line is linear throughout the entire graph. So let's answer some questions here. What is the velocity of the ship in our example? Alright, in order to solve this, we need to pick a couple of points on the graph and then plug into our average velocity formula, which is displacement over the change in time. Alright, this triangle here, I should have told you earlier, that's delta, alright? And that is a Greek symbol, alright? And delta stands for change. And if you are trying to figure out the change in something, it's always going to be the final minus the initial, which is where that comes from. So our final position was, and we're in meters this time, our final position is 20 meters. Our initial position was 10 meters. Alright. And then we're going to look at our x-axis. Remember, y2 minus y1, x2 minus x1, so the y is position, x is time, or position over time. They're the same exact thing. Alright, so time was 2 seconds minus 1 second. Alright, so 20 minus 10 is 10, and 2 minus 1 is 1. So that's 10 divided by 1, which is 10, and then our units are meters per second. So the velocity, the average velocity of this ship throughout the entire trip was 10 meters per second. Alright, remember units for velocity are always meters per second. So let's look at the next question. Will all velocities always be constant? Now they're talking about in real life, not just this graph. Now, we can answer for this graph. For this specific case, will all the velocities of the ship always be constant in this graph? Yes. But now real life, will all velocities always be constant? Or can a velocity change? Can an object speed up or slow down? Yes, an object can speed up or slow down, so no, all velocities will not always be constant. What do you think it would mean if the slope of the line on the graph were steeper? So for example, if it went like this. It's still a straight line. What would you think if it was steeper? Well, let's take a look. What if we selected this point here and this point here? Alright, we would have 40 meters minus 20 meters over, that looks to be about 1 second, minus, at this position, it looks to be about a half a second. Alright, so 40 minus 20 is 20, and 1 minus a half is a half, and 20 divided by 0.5 is 40 meters per second. So what's the difference between this steeper line versus the original line in our velocities? The velocity went up. So we would have an increase in velocity. Alright, so what if the line was less steep? So a more gradual line. Obviously, we would have a decrease in our velocity. Alright, let's suppose that we graph the motion of a boat that is moving at an increasing velocity. Notice that the ship starts at 0, and then in 1 second it travels 2 meters. In another second it travels 6 meters. Another second it's traveled 10 meters. So we can definitely see that this ship is speeding up. Alright, let's track what we get. From 0 to 1 we've got 2 meters, like we said. From 1 to 2 seconds we've got 6 meters. From 2 to 3 we've got 10 meters. From 3 seconds to 4 seconds we've got 14 meters. And from 5 to 4 we've got 18 meters. Alright, so our ship is speeding up. Let's look at our graph here. You'll notice that the slope of this line is curved. It is not linear. Alright, so at 1 second we have 2 meters. At 2 seconds we have 8 meters, just below 10. 3 seconds is 18 meters, just below 20, and so on and so forth. Now, if we want to figure out what the position is, or the displacement between any two sections of time, then we have to look at the distance between them here. Alright, so again, that 50 meters is here, and the 32 meters is here. So the change in position in this section of the graph is worth 18 meters. Alright, that's the displacement between this section of the graph. And it's different for each of these sections. That's what we figured out up here at the top. Alright, now if we wanted to know what the velocity of the ship was in this section, then that's when we need to use our average velocity formula. This would be what would go on top, and then the time would be down here on the bottom, so it'd be the 5 minus 4. So in this section of the graph, the ship was traveling at 18 meters per second. Alright, let's answer some questions. What is the velocity between 3 and 4 seconds? Okay, well, all we have to do is plot the things that we know. We've got this point and this point, and we know that the position of the ship at 4 seconds is 32 meters. So let's write down our equation. The average velocity is equal to the displacement divided by the change in time. So we're going to have 32 meters minus our position at 3 seconds was 18 meters. And then our time was going to be 4 seconds minus 3 seconds. Alright, so let's calculate our average velocity. 32 minus 18 is just what we calculated up here, 14. So 14 meters, and then 4 minus 3 is 1 second. So 14 meters per second is the velocity of the ship in this section of the graph. Remember, I just calculated this one was 18, so we can see the ship sped up and went from 14 to 18. And the question we asked in the previous graph was, what if the slope of the line were steeper? And we said that the velocity would increase. Well, notice that the slope of the line in this section, if we were to extend it, it would be something like this. The slope of this line would be something like this. So it is an increasing line when we go from this section to this section. Alright, and in fact all sections of this graph are increasing, which gives us that curve. Alright, so we can go ahead and write that one down, 14 meters per second, and then between 4 and 5 we said it was 18 meters per second. Alright, I think we'll leave it there for today. Thank you for learning with me, and I will see you next time.